Let us define the following parameters for the van der Pau resistivity measurement. Say rho is the sample density, sample resistivity. It is in ohm centimeter. Then D is the conducting layer thickness, conducting layer thickness. Since we are considering the epitaxial layer only, okay, very thin film layer. So, that is why the conducting layer thickness means the thickness of the epitaxial layer, in this case you can consider, okay, the conducting layer thickness, and this is in centimeter. I12 is positive DC current I injected into contact 1 and taken out of contact 2. Okay. That means it is the direction. When we talk about that, a positive DC current I injected into contact 1 and taken out of contact 2, that means it is the polarity of the current. So, that means if you reverse the polarity, that means in that case the current will be I21 instead of I12. Instead of I12 it will be I21, and that means the current will be injected at terminal 2 and will be taken out at terminal 1. So, that means it is the reverse polarity of the current. So, I2 is the positive DC current. Similarly, I23, I34, I41, I21, I14, I43 and I32, all in ampere. That means how much current do you have? 8. How much current do we have? You find how many? 8. I12, I23, I34, I41, I21, I14, I43 and I32. So, 8 currents we have to measure. 1 2, if 1 2 is the positive, then 2 1 is the negative. Then if I say 2 3 is the positive, then 3 2 is the negative. If 3 4 is the positive, then 4 3 is the negative. If I 1 4 is the positive, then 4 1 is the negative, or the vice versa. So, that means finally you have to measure 4 current, but if you use a constant current source, then you apply current from a constant current source. That means these values are your predetermined values. You will send the current 1 microamp, 1 milliamp or 1 nanoamp, whatever be the case, it depends on the resistivity. Okay. So, 8 currents you have to consider. Similarly, the voltages, actually you have to measure the voltage. You are giving the current and the corresponding voltage you are recording. So, for voltage measurements, this thing we can consider, that apply current I2, measure voltage V34 under this configuration, reverse the polarity, current will be I2 and the voltage will be V43. Repeat for V41, V14, V12, V21, V23, V32. Here also you find that 1, 2, 3, 4, 5, 6, 7 and 8, 8 voltages are there, because for 8 current you will get 8 voltage, right. So, you send current, you record the voltage straight away, there is no ambiguity in it, and the configuration is in the counterclockwise direction. If you take this one as the 1, then it is 2, 3 and 4, these are the small ohmic contacts. Small means the diameter is of the order of 1 millimeter. Then the next thing is that there will be 8 resistance, because 8 voltage and 8 current you got. So, when you divide that voltage with current, you will get the resistance. So, you will get 8 resistances. Let us see a R2134, that is resistance, it is V34 by I21. Similarly, R1243, that is equals to V43 by I12. R3241, that means V41 by I32. R2314, that means V14 by I23. Similarly, R4312, that is equals to V12 by I43. R3421, that means V21 by I34. R1423, that is equals to V23 by I14. R4132, that is equals to V32 by I41. So, these are the resistances you get from the measurement of 8 current and voltage. Clear up to that point? It is clear? Just simply we have taken the ratio, and you see that R21 means we have marked the resistance, or we have denoted the resistance by 2 numbers 21, 34. 21 is the current, 34 is the voltage. Here you see that R34 is the current, 21 is the voltage. First we have used the current, the next number is the voltage. You can determine by R1, R2, R3, R4, that is also possible. Okay, not necessary that you have to mark in this manner. Now, you get 4 resistances, 8 resistances, then you have to check for the consistency of the measurements. That is very important, because you cannot take any value for the resistances. How to check the consistency? That is the most important part of this measurement. Otherwise, there is nothing in this kind of measurement. Only the consistency part. The consistency part is that check consistency. Check for consistency. R2134 must be equals to R1243. R4312 must be equals to R34 R3421. Similarly, R3241 must be equals to R2314 and R1423, that is equals to R4132. This is condition 1. And condition 2. R2134 plus R1243 must be equals to R4312 plus R3421 and R3241 plus R2314 must be equals to R1423 plus R4132. These two conditions must be satisfied. Okay. So, if you want to check the consistency, you check in this manner. You have 8 resistances, you see whether this resistance is equal to that resistance or whether this resistance is equal to that resistance, or if you add these two resistance, whether their total value is equals to the sum of the two resistances R 4312 and R 3421. So, these are the consistency checking. Okay. Now, what is the tolerance limit? What is the tolerance limit? Within 5%, this must be equal, within 5%. Better for very good result, if you want precision, then within 3% this must be true, right. So, that means if the variation is more than 5%, you must be sure that there must be some error in the measurement. There must be error in the measurement if this is more than 5%. What is more than 5%? Suppose this is 10. What should be the value of R 1243? 9.52 at the most. If you want precision, 9.7 to 10.3. So, if it is 10, its value must be within 9.5 to 10.5. So, such kind of precision is required and we can allow tolerance up to that limit. If you find that it is 10 and it is 17, or if it is 15 and it is 12, then you see that what actually happens in your measurement. I understand. then be sure that there has some error in it, and so the final result will not be very encouraging. Okay. Now, this is our, you see that this is our expression. We are very close to solve this expression, because that is the Van der Pau equation. We want to determine R s, provided we know R A and R B. To determine R A and R B, we have calculated 8 resistances and we have checked their consistency as well. Now, R A and R B. R A equals to R 2134 plus R 1243 plus R 4312 plus R 3421 by 4, and R B equals to R 3241 plus R 2314 plus R 1423 plus R 4132 by 4. Right. So, if you know R A and R B from this equation, you can use this expression to calculate the seat resistance using Van der Pau equation. That means, you have to solve it numerically, numerical solution, otherwise how you will solve it. That means, you have to make a very small computer program and you have to take the advantage of the iteration, because you see that this plus this will be 1. So, every time you have to calculate this thing with that thing and you have to take the difference and whether that is very close to 1, right. So, likewise, using a very small computer program which is known as the numerical solution, because analytically you cannot solve this result. Analytically, it is not possible to solve this equation. So, normally you have to use a numerical solution, right. If you can, you can, everything is there with Mohandas. So you can take the data. Okay. So, numerically you can solve this equation to achieve at R s. Once you know the R s, the seat resistance, the seat resistance you know, then resistivity, bulk resistivity, rho equals to R s into d. D is the thickness of the layer D is the layer thickness. You see that D is the conducting layer thickness. So, if you know D, you can measure the bulk resistivity. So, you have two options. One is, first you consider a very thin sheet of material at the top, consider, then measure the sheet resistance using Van der Pau equation, and then multiply that sheet resistance with the thickness of the material to get the bulk resistivity of the material. Okay. So, that is in a nutshell the calculation of the resistivity by Van der Pau method. It is not straightforward. The 4-point probe is straightforward. So, when only the precision result is required, when your sample needs to be characterized very precisely, then you adopt Van der Pau technique. Otherwise, you can go for the 4-probe method. But if your sample is very high resistive, then 4-point probe method will not give you any result also. Then you have to measure using a Van der Pau configuration. Okay. So, these are the two techniques using which we have measured the resistivity. You see that we have started our discussion with the measurement of resistivity. This is the resistivity. Now, so far as the carrier concentration, mobility and type of conductivity is concerned, you have to use the Hall effect measurements. Hall effect measurements. And Hall effect measurements, you know that you have to make use of a magnetic field.
Sir, one question.
Yes.
If we have a contact of aluminum and silicon,
You have a contact between aluminum and silicon. Yes.
under what condition it is a Schottky?
No, that we shall discuss. It depends on the work function of the metal and the semiconductor. It depends on the work function of the metal and semiconductor. If you join, suppose let me just explain in this way. Suppose this is your metal, left side is metal and this is semiconductor. This is Fermi level for metal, this is Fermi level for say n type semiconductor. Here you see that with respect to some vacuum level, this is small compared to semiconductor, that work function is small in case under this situation. So, the metal electrons, yes, will be able to go for this side. Okay. Now, the question is that under such a circumstance, when there will be equilibrium, then there will be a barrier. Okay. How long they will go? Yes, unless they are equal, then the Fermi level will align and then there will be a potential barrier as usual. So, then it will not move to that side. So, the free movement of the electrons are not possible under such configuration.
Under such condition it is Schottky?
Yes, it may be Schottky, it may not be Schottky, but it is non-ohmic in nature. Sometimes you will find that the actual Schottky curve is like this, but in some cases you will find that it is like this or it is like this. Then this is not a perfect Schottky. This is not a perfect Schottky. This is non-ohmic in nature. Then we have to study what type of thing, whether it is due to thermionic emission or generation recombination or the some heterostructure type of conduction. There are many conduction in semiconductor. One is ohmic, another is Schottky, but apart from that you can consider different kinds of mechanism also or a mixed mode conduction mechanism. In some cases hopping conduction takes place. So, there are many various transport mechanism in semiconductor, but that will be non-ohmic in nature. Okay, now, in Hall effect, generally we put a magnetic field and a current is passed through the material and the magnetic field is perpendicular to the direction of current. Then a Hall field is generated. That field is mutually perpendicular to both the magnetic field and the electric field. Okay? And that field is known as the Hall field, which is generated. It comes from the Lorentz force. Current and magnetic field is there. So, it will be Q into V cross B, Q into V cross B, and obviously these are the vectors. In one dimension we can consider that it is V into B in one dimension. Particular for a particular one dimensional case, this can be replaced by the dot product, not the cross product. Now, you see that suppose you have a this type of a semiconducting bar, or let us consider that this is a metal bar. Let us consider that this is a metal bar, forget about semiconductor in the first case. The current passes through this x direction, positive x direction, it is say it is the positive x direction, and the magnetic field is in the which direction? Z direction. So, the Hall field will be developed in the y direction. So, first what will happen when the current will pass through the semiconducting material, the electrons will move towards the bottom and the holes or the positively charged ion, say in case of metal there is no holes. So, only the say if it is a copper, so there will be Cu2 plus copper ions. So, those are the uncompensated ion which will be on the upper side. It is because of the magnetic field that the force due to the magnetic field, Lorentz force, they will push the positive particles upward and the negative particle downward. So, there will be a, you can consider that there will be a dipole type of array situation or arrangement. Under such a circumstance, an electric field will be generated, and that is why this EH will be generated, which is the Hall field. It is because of the Lorentz force. And you see that how long this positive and negative polarization will be there? How long? Yes, when the electric field will be equals to the force due to the magnetic field. So, that means when in this case, in this case you see that E H equals to E V dx B z in this case. In this particular case you see that E H, that means this is the force, E H is the field. When the field is multiplied by the charge, it becomes force, and here also this B z is the magnetic field and Lorentz force is E V B z. So, under such a circumstance when they will be equal, such kind of polarization will be stopped. So, polarization will be available till this field is not perfectly balanced. When it is not balanced.
Sir, current is flowing from left to right.
Yes. So, electrons are flowing, current is flowing, yes. So, the electrons are flowing in the negative x direction. The electrons are flowing in the negative x direction.
So, the force, Lorentz force on electrons will be downward.
Yes, yes,
And holes are flowing in the positive x direction.
yes. It is metal. It is metal, not it is semiconductor, because the discussion is very becomes convincing if you use a metal, because first the Hall effect was discovered in probably 1829 or such in a metal only, not in a semiconductor. Then we have used the theory of Hall effect in semiconductor also. So, this type of a situation will be there when E E H equals to E V dx into B Z, or if you use a standard phenomena, we can write down that E, or say it is Q E y is equals to Q V x into B z. You see that V x is the drift velocity, it is in the positive x direction, because the electric field was in the positive x direction, and Q is the charge, E y is the Hall field generated in the y direction, and B z is the magnetic field, or E y equals to V x into B z. Okay. Now, you see that this is equals to E y equals to V x B z by E y. What is V x and what is E y? Hmm? V x equals to E y. What is E y?
No, no, sir. In left side, EY equal to Vx, Vz by EY.
Yeah, yeah. Then what is V x? And now I have to calculate the V x to determine E y. Okay. So, E y equals to V x into B z, and V x equals to, you know that J equals to N E V, right. So, you can replace this V x by J by N E, or if you use the current, then I by A N E into B z.
N is upper side.
No, it is okay, it is correct. That means J into B z into 1 by N E. E y equals to this, or we can write E y equals to 1 by N E J into B z, that means equals to R h J into B z, or R h is equals to 1 by N E. R h equals to 1 by N E. This is known as the Hall coefficient. Obviously, if this is an n type semiconductor, this will be negative, because the charge is negative. If you take a p type material, then it becomes positive, that means R h equals to 1 by p into E. R h is equals to 1 by p into E.
Again, we considering the metal, then how n type of it.
It is only electrons are there, only electrons are there. So, it is okay, up to this point it is over. But if you take a p type semiconducting bar or an n type semiconducting bar, then the only difference will be that the Hall coefficient will be positive for p type semiconductor and it will be negative for n type semiconductor because of the charge consideration. For metal it is always negative, but there is one difference, in beryllium it is positive. For metal, because of its band theory, it comes from its band theory. You can explain that nature of that Hall coefficient from the band theory. It is, I can give you the value, let me give you the value. B beryllium, its value is plus 3.4, RH is plus 3.4. This is due to band theory of solid, we are not going into consider. Okay. So, under this circumstance you can calculate the Hall mobility. You see that once you know the Hall coefficient RH, you can calculate the carrier concentration, either it is P or N, carrier concentration. Why? If you can measure RH, that is equals to 1 by P into E, E is the electric charge which is known. So, once you know the Hall coefficient, you can measure the carrier concentration and also the polarity, that means the conductivity type. If the Hall coefficient is positive, then the conductivity type is N type, is governed by the electrons. If it is positive, if the Hall coefficient is positive, then the material is P type, that means it is governed by the conduction of holes. So, depending on the polarity of the Hall coefficient, you can consider whether it is positive P type or N negative N type. So, the type and the conductivity, that means N or P, as well as the carrier concentration can be calculated from the Hall effect. Now, how you can calculate the mobility?
So, my question was for semiconductor.
Yes.
In semiconductor, the holes and electrons both are depositing on the bottom.
Both the will be a top side also. Why? Because there will be uncompensated charges as well. When in a semiconductor, there are 4 types of situation. One is electron, another is hole, third one is the uncompensated positive charge, and fourth one is uncompensated negative charge, that means the ions. So, 4 types of consideration is there, and I can give you the reference, you write down so that you can go through it. You write down, it is the book of S.O. Kasap, and the page number is it will be say 150 or such, page 150 to 155 you will find how in a semiconductor the Hall effect is explained. Okay, that is given, and in terms of P and N it is given. That is a long calculation, and we are not going into those details thing, because that is not required also. If both the carriers are there in a semiconductor, you know that though the majority carriers are N, there are some minority carriers of P, or the vice versa.
So, in metals, the voltage generated due to the deposition of negative charge on the
Yes.
and positive on the top. So, electric field is generated. In semiconductor, both the charges are depositing on the bottom. So
No, in semiconductor, if it is an N type semiconductor, you can consider it is like a metal. If it is an N type semiconductor, then for all practical purpose, you can consider the theory of the metal to be applicable in case of N type semiconductor. Only the uncompensated charges will be on the surfaces. In metal also, you find that if you take a copper sample, the electrons will be deposited on the bottom, and what will be there in the top? It is the uncompensated or the positive ions, copper positive ions, that will be there. When electrons will leave, that means positive ions will be generated. So, one electron in the bottom means one ion, positive ion in the top. So, thereby the field will be generated. In N type also, the electron comes from the ionization of the donor impurity, the same thing will happen. And if you need more discussion, you consider S.O. Kasap, page 150 to 155. Okay. Now, let us discuss about the mobility. You know that sigma equals to N E mu. N you can calculate from the Hall effect. E is the electronic charge, And what is sigma? Sigma is the conductivity, it is inverse of resistivity, and resistivity is measured from the Van der Pau or the 4-probe method. So, if you use a Van der Pau configuration to measure the Hall effect, then it is better to use the Van der Pau configuration, because for Hall effect you need to use the Van der Pau configuration. So, thereby you use the Van der Pau configuration, you measure the and then calculate the mobility. That mobility is known as the Hall mobility. Obviously, it is from the Hall effect, it is the Hall mobility. So, that means from a semiconductor piece you can determine all the parameters, the resistivity, carrier concentration, mobility and type of conductivity. Those 4 things are the basic characteristics of a electronic material. Not don't mix up with other materials which is say structural or organic or polymeric, not that. Here the concept is the electrons, because it is we are interested about its application in the electronic field, in electronic applications. So, these 4 very basic characteristics are can be recovered from the electrical characterization if you have Van der Pau and Hall setup, and very simple also.
Any difference between the Hall mobility and general
Drift mobility.
drift mobility?
Yes, that is difference, but drift mobility you cannot determine directly. Mobility can be, because when we measure the mobility, it is basically the Hall mobility. So, if you say that the mobility of electrons in silicon is 1300 centimeter square per volt second, that means it is the Hall mobility, because directly the mobility can be determined from the Hall only. Whether it is mentioned or not, that is a different story, but it is basically the Hall mobility. From the drift of the electrons, there is a drift mobility also, the concept is there, but you cannot measure that thing directly. Okay. Now, if you go for this numerical problem, then you can clear some of the concepts. A 4-point probe with probe spacing of 0.5 millimeter is used to measure the resistivity of a p-type silicon. Find the a 4-point probe with probe spacing of 0.5 millimeter is used to measure the resistivity of a p-type silicon sample. Find the resistivity of the sample. Okay. Find the resistivity of the sample if its diameter is 200 millimeter and its thickness is 50 micron. There are two same, it is repeated, find the resistivity of the sample, find the resistivity of the sample. If it is diameter is 200 millimeter and its thickness is 50 micron, the contact current is 1 milliampere given, and the measured voltage between the inner two probes is 10 millivolt, it is also given. That means current is given, voltage is given, thickness is given, diameter is given and probe spacing is given. So, using 4-point probe method, you have to measure the resistivity of the p-type silicon sample. So, that is all. You write down in short, because this slide you will get, you can copy it from the computer. So, absolutely do not waste your time in writing, only in shorthand, just current is there, voltage is there, thickness is there, diameter is this and probe spacing is this, what is the rho, you have to calculate rho only. You calculate the rho.
So diameter 200 mm means it is circular.
Obviously, the diameter means that it is circular in nature. I hope so.
Simply you have to measure in ohm centimeter or ohm meter.
That is your choice, either in ohm centimeter or in ohm meter. There are two possibilities. is V is given 1 milliampere, it is 1 into 10 to the power minus 3 ampere. Then sorry, it is I. V is given, V is how much? 10 millivolt, that is 10 into 10 to the power minus 3 volt. Then what is the thickness? Thickness T is given, it is 50 micron, that means how much? 50 into 10 to the power minus 4 cm. And one thing you need, it is the correction factor. What is the correction factor? Yes, 4.53. Why it is 4.53? Huh? No, that is pi by ln2 is the for circular sample, but here why it is so? Yes, basically here the diameter, you see that to solve this type of a problem, diameter has no use in the equation. Okay? Is it there in the equation? No. Then why it is given? It is given to ensure that the diameter is very greater than the probe spacing, and also the thickness. Here the probe spacing is 0.5 millimeter. So, 200 millimeter is very greater than 0.5 millimeter. Even suppose you are using a rectangular or square samples, if you find that the thickness is very greater than the probe spacing, then you cannot use 4.53 as the correction factor. But if the thickness is less compared to your probe spacing, the probe spacing is generally 1 millimeter. Here it is given 0.5 millimeter, but generally it is 1 millimeter. And what is the thickness? If you use a thin film sample, the thickness is 1 micron or even less than 1 micron. So, 1 micron is less than probe spacing, then you can use 4.53 as the correction factor. But if the probe spacing is less compared to your thickness, then you cannot use, that means for bulk sample.
It is given there in our condition.
It will be given probably, or you have to justify why you are taking that value. In most of the cases you will find that you can use 4.53, most of the cases, because the probe spacing is large compared to the thickness. Then what is the value? 1.42.
2.26 minus 3.
Yes, so that means rho equals to V by I into T into correction factor. This is equals to 10 into 10 to the power minus 3 by I is 1 into 10 to the power minus 3 into 50 into 10 to the power minus 4 multiplied by 4.53 or 54, and you will find that it is 226 ohm centimeter, 0.226 ohm centimeter.
I calculate the resistivity from the formula R A by L, R into A by L.
What is your value?
R equals to I.
What is your rho value? Value of rho.
Rho value is coming 2.5 into 10 to the power 4 ohm meter.
Then in ohm centimeter, what is the value?
Will be in 6.
Hmm?
10 to the power 6 ohm centimeter.
So that is wrong, because you have to use the formula for the 4 probe not the formula designed by yourself. then why you use the 4 probe or van der Pau?
R above equals R into A by L. L is the thickness, A is the area. That is for ohmic conductor.
That is for ohmic conductors. Cleverly, we have used that value also, because rho into R into A by L, but generally that is valid for ohmic conductor. For ohmic conductors, you need not to use any 4 probe or van der Pau configuration. It is very straightforward. Just by 2 probe, that means you send voltage and get the current, and you take the ratio, you will get the resistance. Okay. Then there is another problem, which is this one, that given a silicon sample of unknown doping, Hall measurement provides the following information. You just write down the data: W equals to 0.05 centimeter, A the area equals to 1.6 into 10 to the power minus 3 centimeter square, I the current is equals to 2.5 milliampere, and the magnetic field is 30 nano Tesla, and 1 Tesla is given, it is 10 to the power minus 4 Weber per centimeter square. If a Hall voltage of plus 10 millivolt is measured, find the Hall coefficient, conductivity type, majority carrier concentration, resistivity and mobility of the semiconductor. Many things we have to determine. Okay. It is given that W equals to 0.05 centimeter, area is 1.6 into 10 to the power minus 3 centimeter square, I equals to 2.5 milliampere, and magnetic field is given 30 nano Tesla, and Hall voltage is given. You have to calculate RH, Hall coefficient, conductivity type, majority carrier concentration, that is N or P, resistivity and mobility. Okay. So, you try. Yes, what is W and what is A, it is given, you see, with it is relative to this figure. A is the area and W is the thickness basically here. Now, first tell me what is the carrier type, it is P or N?
It is denoted by RH.
Yes.
If RH becomes positive, then it will be P type.
Now what is there for RH? What are the
UI by JVZ, and now UI is G by
no, you see that the polarity of RH will depend on which factor? You see the equation, you see the relation.
Relation is VH into W into A upon I into B.
Then on which factor the polarity of RH will depend?
I and I.
It will depend on the VH Hall voltage. It will depend on the hall voltage. Now, hall voltage is given, how much it is?
10 millivolts.
It is plus or minus.
Plus
So,
P type.
it is p type, obviously it is p type. You see that it is R h is equals to V h into A by I B z into W. Can we write? R h equals to V h into A by I B z W with reference to this figure you see.
So 1.07
I can write. Okay. So, that means V h is 10 milliampere. What is the area? 1.6 into 10 to the power minus 3. Current is 2.5. Magnetic field is 30 nano Tesla, that means 30 into 10 to the power minus 9 Tesla into 10 to the power 4 Weber per centimeter square into W is 0.05. That means it is 426.7 centimeter cube per coulomb. So, here R h is positive. So, the Hall, yes, so that means the carrier concentration is positive, that means the sample is p type and the carriers are holes. Then what is the hole concentration? This one, P equals to 1 by Q into R h. So, 1 by 1.6 into 10 to the power minus 19 multiplied by 426.7 and it comes out to be 1.46 into 10 to the power 16 centimeter cube inverse. We have done.
So 1 Tesla is constant for minus 4 Weber per centimeter square or plus 4?
Plus 4. Plus 4. Tesla is high. 10 kilogauss equals to 1 Tesla. Okay. So, three things we have calculated. One is the Hall coefficient, the type and the carrier concentration. But for the determination of mobility, you must know the resistivity, okay? And the resistivity is not given. So, basically there will be a chart like this from where you can calculate the resistivity. Here what is the carrier concentration? 1.46 into 10 to the power 16, 10 to the power 16, that means this is 10 to the power 16. And what is this sample, silicon or gallium arsenide? Silicon. So, that means this is p type silicon, this is p type silicon. So, it becomes normally from the graph we find that it is 1.1 ohm centimeter precisely, rho is 1.1 ohm centimeter. In exam such graph will not be given, so the value will be provided. Otherwise, you have to take the value from a graph. But data sheet is available, for all material data sheet is available. So, if you know the impurity concentration, from the impurity concentration you can find the resistivity, and from the resistivity you can measure the mobility. Mobility is equals to mu equals to 1 by q into p into rho. Now, what is q? Q is 1. Yes, mu equals to 1 by q into p into rho, 1 by 1.6 into 10 to the power minus 19, p is 1.46 into 10 to the power 16 and it is 1.1 rho, that is equals to 380 centimeter square per volt second. So, this is an example using which you know that you are in a position to determine the material parameters of a p or n type semiconducting sample which is essential for the for its application in electronic industry. Okay. So, that is very important. Suppose we have grown a very good silicon, you claim that it is good silicon and you find that its mobility is in place of 1300 it is say 800. So, that means what is that? It is very bad material. It is of no use, it has no use, you cannot use that material, because the standard silicon has 1300 centimeter square per volt second is the mobility and your grown material is 800 only. Okay, that means it is a bad material, some impurities are there, right. So, with this we conclude our discussion for today. Next day we shall concentrate on the optical characterization of the materials.